When we look up at the night sky, we see countless points of light. These twinkling wonders are stars, giant balls of hot gas that light up the universe. Stars are incredibly far away, but their light travels across vast distances to reach us here on Earth. They come in different sizes and colors, each with its own story to tell. Stars are not just pretty lights in the sky. They play a vital role in the universe. They are the cosmic engines that create the elements necessary for life. The very atoms that make up our bodies were once forged in the heart of a star. Throughout history, humans have been fascinated by stars. We have used them for navigation, told stories about them, and studied them to understand the universe better. Stars continue to inspire us with their beauty and mystery. Our sun is a star, a rather ordinary one compared to some of the giants out there, but it is the closest star to us and the source of energy that makes life on Earth possible. Stars are not scattered randomly throughout space. They are born in vast clouds of gas and dust known as nebulae. These nebulae are like giant stellar nurseries where the ingredients for stars come together. Nebulae, often called clouds in space, are spread out over vast distances. They are composed mainly of hydrogen and helium, the two most abundant elements in the universe. These clouds are cold and dark, but within them, the seeds of stars are sown. Within these nebulae, regions of slightly higher density begin to clump together. This clumping is random, driven by turbulence within the cloud. As more and more material accumulates, these clumps grow larger and denser. These dense clumps are the starting point for star formation. They are called protostars, the precursors to fully formed stars. The journey from a dense clump of gas and dust to a shining star is a fascinating one. Gravity plays a crucial role in the birth of a star. As the clumps of gas and dust within a nebula grow larger, their gravitational pull increases. Gravity acts like a cosmic sculptor, pulling material inward toward the center of the clump. As more material falls inward, the protostar at the center becomes hotter and denser. The temperature and pressure at the core continue to rise as gravity relentlessly pulls in more gas and dust from the surrounding nebula. This process of gravitational collapse continues for millions of years. During this time, the protostar is not yet a true star. It does not generate energy through nuclear fusion, the process that powers stars. Eventually, the core of the protostar becomes so hot and dense that nuclear fusion begins. Hydrogen atoms fuse together to form helium, releasing tremendous amounts of energy. At this moment, a star is born. Once nuclear fusion ignites in the core of a protostar, it becomes a true star. It enters a relatively stable period of its life known as the main sequence. Our sun is currently in its main sequence phase. During the main sequence, a star fuses hydrogen into helium in its core, producing the energy that makes it shine. The outward pressure from this energy balances the inward pull of gravity, keeping the star in equilibrium. The length of time a star spends on the main sequence depends on its mass. Massive stars burn through their fuel much faster than smaller stars. Our sun, a medium-sized star, will spend about 10 billion years on the main sequence. As a star ages, it gradually exhausts the hydrogen fuel in its core. Once the hydrogen in the core is depleted, the star begins to evolve away from the main sequence, entering the later stages of its life. These later stages are marked by dramatic changes in the star's size, temperature, and luminosity. The star's fate ultimately depends on its initial mass. Section 5. The main sequence, stellar adulthood. The main sequence is the longest and most stable stage in a star's life. Stars fuse hydrogen into helium, generating energy. Stars exhibit a relationship between mass and luminosity. More massive stars are hotter, brighter, and bluer. Our sun is halfway through its main sequence lifetime. Red dwarfs are cooler, fainter, and have long lifespans. Massive stars live fast and die young. Main sequence stars produce heavy elements essential for life. Section 6. Red giants when stars expand. As a star nears the end of its main sequence lifetime, it begins to run low on hydrogen fuel in its core. The core contracts and heats up, while the outer layers of the star expand outward, causing it to swell into a red giant. Red giants are much larger and cooler than main sequence stars. They have a reddish appearance due to their lower surface temperatures. Betelgeuse, a bright red star in the constellation Orion, is a well-known example of a red giant. During the red giant phase, a star's core continues to contract and heat up. Eventually, the core becomes hot enough to ignite the fusion of helium into heavier elements, such as carbon and oxygen. The helium-burning phase is much shorter than the hydrogen-burning phase. As the helium in the core is depleted, the star's structure becomes unstable, and it begins to pulsate and shed its outer layers into space. These ejected outer layers form a beautiful expanding shell of gas and dust known as a planetary nebula. The planetary nebula is illuminated by the hot, exposed core of the star, creating a cosmic spectacle. Section 7: Stellar Endings, White Dwarfs, Neutron Stars, and Black Holes. The final fate of a star depends on its initial mass. Low-mass stars like our Sun end their lives as white dwarfs. More massive stars explode as supernovae. The core collapses, forming either a neutron star or a black hole. Section 8: The Circle of Life, Stellar Recycling. The death of a star is not the end, but rather a beginning. The material ejected from stars during their lifetimes and at their deaths enriches the interstellar medium, the space between stars, with heavier elements. These heavy elements, forged in the hearts of stars, become the building blocks for new generations of stars and planetary systems. Our own solar system formed from a cloud of gas and dust that was enriched by the remnants of previous generations of stars. This recycling of stellar material is essential for the chemical evolution of the universe. Without the deaths of stars, the universe would be a rather dull place, devoid of the heavy elements that make up planets, life, and even ourselves. The atoms in our bodies were once part of stars that lived and died long ago. We are literally made of stardust, connected to the vast cosmic web of stellar birth, life, and death. Understanding the life cycle of stars gives us a profound appreciation for the interconnectedness of the universe and our place within it. Section 9: Star Clusters, Families of Stars. Stars are not always found in isolation. In fact, most stars are born in clusters, groups of stars that formed from the same cloud of gas and dust. These clusters provide valuable insights into the processes of star formation and evolution. There are two main types of star clusters: open clusters and globular clusters. Open clusters are relatively loose collections of stars, typically containing a few hundred to a few thousand stars. They are often found in the spiral arms of galaxies, where star formation is active. Globular clusters, on the other hand, are much denser and more tightly bound. They can contain hundreds of thousands or even millions of stars packed into a relatively small volume. Globular clusters are typically much older than open clusters and are found in the halos of galaxies. By studying star clusters, astronomers can learn about the ages, compositions, and dynamics of stars. Clusters provide a snapshot of stellar evolution, allowing astronomers to study stars of different masses and ages that formed in similar environments. Section 10: The Milky Way, Our Galaxy of Stars. Our Sun is just one of billions of stars in the Milky Way galaxy, a vast spiral galaxy that spans over 100,000 light-years across. The Milky Way is home to a diverse population of stars, from faint red dwarfs to luminous blue supergiants. The Milky Way is thought to contain a supermassive black hole at its center, with a mass millions of times greater than our Sun. This black hole, known as Sagittarius A*, is surrounded by a swirling disk of gas and dust. The Milky Way is constantly evolving, with new stars being born in its spiral arms and older stars ending their lives in supernova explosions or as white dwarfs. The galaxy is also on a collision course with its neighboring Andromeda galaxy, a collision that is predicted to occur in about 4 billion years. Studying the Milky Way helps us understand the formation and evolution of galaxies, the distribution of stars and gas, and the nature of dark matter, a mysterious substance that is thought to make up a large portion of the universe's mass. Section 11: Conclusion: A Universe of Wonder. Stars are more than just twinkling points of light in the night sky. They are fundamental building blocks of the universe. They are the cosmic engines that forge the elements necessary for life, and their life cycles drive the evolution of galaxies. From their birth in stellar nurseries to their explosive deaths as supernovae, stars captivate our imagination and inspire us to learn more about the universe we inhabit. Their beauty and mystery remind us of the vastness of space and the intricate workings of the cosmos. As we continue to explore the universe, stars will undoubtedly continue to amaze us with their diversity, complexity, and sheer power. They are a testament to the wonders of the natural world and the endless possibilities that lie hidden among the stars.